A particle of mass 6 kilograms is on a rough plane inclined at 30 degrees to the horizontal. Josh is pushing the particle with a force of magnitude J newtons in a horizontal direction. And that horizontal direction is in a vertical plane parallel to the line of greatest slope of the inclined plane. Given that the coefficient of friction between the particle and the plane is 0.8, find the range of possible values for J. And actually, I've printed this sheet out. I should have also had in there that the particle is in equilibrium, okay, because we're in the statics chapter. Okay, so I'm going to start. There's a few different situations that could be happening here. I'm going to start by drawing in some of the forces that are going to remain unchanged. So you've got the normal reaction and the weight. Now the weight is going to be a mass of 6, so a weight of 6g. We know that we've got 30 degrees here, and we're going to put in here that this is 30 degrees. And then we've got a horizontal pushing force from Josh. Now Josh's horizontal pushing force could be pushing that way, so pushing into the slope, or it could be pushing that way, pushing away from the slope, so into the slope or away to the slope. And when we are pushing down the slope, so away from the slope, pushing in that direction, the only possible way that particle goes go down the slope, so the friction would be up the slope. And we'll come back to that one right at the end. When I'm pushing this way, when Josh is pushing this way, he could be pushing really hard, so it's about to move up the slope, or he could be just pushing a little bit, just holding in with enough force that it doesn't fall down the slope, so it's quite heavy, and he's just lightly holding it so that it's about to fall down the slope, but he's stopping it from doing that. So we're going to look at those two situations and then come back to the third situation. So we're going to have a pushing force from this side, but we're going to draw it as a pulling force on this side. And in this case, we're going to say he's about to push it up the slope. It's on the point of moving up the slope. Or the potential motion is up the slope, I suppose we should say, because it's in equilibrium. And this is the friction. So he's pushing it with enough force that this, the component of the J force up the plane is bigger than the component of the weight force down the plane. So the potential motion is up, so the friction is down. But as I said, we can have the other situation, so let me quickly fill in for R. Whilst I'm doing this, I suppose you could maybe work out what are the values of J that gives the situation on the left, and what values of J give the situation on the right. That's something we'll come back to at the start. Come back to at the end. So we have 30 degrees in here, 30 degrees in here. We also have this 30 degrees now, and we're ready to start resolving the particles. We've been asked to work out the range of possible values for J. Well, the one thing that we know, because the particle is in equilibrium, we know that the friction has got to be less than or equal to mu r. So what we're going to do, the big picture, is that we know that this is 0.8, and the friction is going to be written in terms of J's and G's, and we can find R in terms of J's and G's. Substitute into this inequality and then rearrange it for J. That's the big picture. So we're going to resolve away from the plane and into the plane, so perpendicular to the plane, and we're going to resolve parallel to the plane, so that we get equations for J and for F and for R, and they're going to be in terms of J. So let's resolve the particle. We know that the force is let's start that a bit further over actually. the forces away from the plane are going to equal the forces into the plane. Now in this case the forces away from the plane are just going to be R, and the forces into the plane is going to be 6g cos 30 plus j sine 30, because that's going to be opposite. So we've got making a triangle of components. This one is opposite the 30, so it's going to be j sine 30. So just replacing cos 30 with root 3 over 2 and sine 30 with a half, I end up with r equals 3 root 3g plus half of j. And actually resolving in this direction gives the same equation, the same situation as resolving here, because the friction up the plane here and the friction down the plane, it doesn't act perpendicular to the plane. So the situation is the same for both here. So I can just maybe copy that across right away and say that r equals 3 root 3g plus a half j. Okay, now we're going to resolve the particle, and we're going to look at the forces down the plane, or forces down the plane equal the forces up the plane. So we're resolving parallel to the plane. Now the forces down the plane in this case are F plus this bit, so that's going to be F plus 6g sine 30, and the forces up the plane are going to be J cos 30. So I can make F the subject, and again replacing sine 30 with a half and cos 30 with root 3 over 2, I get, and let me write this way here, so root 3 over 2j take away 3g. And we're going to come back and we're going to have to do this separately for this part, because now the friction's in the other direction. So we'll come back to this. So for now, we know that because it's in equilibrium, I know it doesn't say it in the question, but it should do, the friction has to be less than or equal to the limiting friction, so less than or equal to mu r. So we know that F is less than or equal to mu r, but we know that the friction is root 3 over 2 j take away 3g, which is going to be less than or equal to 0.8, it says that in the question here, 4/5, and then r, which is 3 root 3 g plus a half j. So now rearrange it and get all the j's onto the left hand side. We're going to actually what I'm going to do is get rid of this denominator by times it by 2 and this one by times it by 5. So I'm going to times the whole thing by 10. So I'm going to times the whole thing by 10 and get the j's across the left hand side. So times that by 10, I get 5 root 3 j. Times this by 10 and get it onto the right hand side, I'm going to get 30g. If I times this by 10, that turns into an 8. So I've got 8 lots of this. So that's going to be 24 root 3g. And 8 lots of this would be 4j. Taken away from the other side, or taken away from both sides, is minus 4j. And if I stick that in my calculator, factorising out the j, and doing this divided by the factorised part, 5 root 3 take away 4, I get an answer of, to 3 significant figures, 151 newtons. Okay, so that's saying that Josh can be pushing into the slope up to 151 newtons and the particle won't move. As soon as he goes beyond 151 newtons, it will start going up the slope. But the friction is acting down the slope because it's opposing that possible motion. Now on this side, I have the friction going up the slope because it's about to fall down. So it must be a heavy weight compared to how much Josh is pushing. So he's not pushing very much. So what we're going to do now is resolve particle again with the forces down equaling the forces up. The forces down in this case are going to be just 6g sine 30. And that's going to equal the j cos 30 plus F. Okay, so I can rearrange this equation to make F equal to, again replacing sine 30 with a half, I get 3g, and then cos 30 is root 3 over 2, so take away root 3 over 2j. And again, I know that F is less than or equal to limiting friction, and I can substitute in F on the left hand side, which is 3g take away root 3 over 2j, and that's got to be less than 4/5 of r, which is just the same as before. And now when I rearrange it, again timesing by 10 and getting all the j's onto the left hand side. In fact, I'll leave the j's on the right hand side, I think. So I'm going to get times by 10, I'll get 30g, times this by 10, and I'll get 5 root 3. So 5 root 3j. Times this by 10 makes 8. 8 of these are 24, so 20, take away 24 root 3g, and then times this by 8 just gives 4j. So this time, if I do 30g take away 24 root 3g, I actually get a negative answer. And when I divide that by 5 root 3 plus 4, I end up with j being greater than minus 8.96. Okay, so the actual answer for this particle to be in equilibrium is that j has to be between minus 8.96 and 151 newtons. In other words, Josh can be pushing, J is away from the plane with J less than or equal to 8.96. So this negative just means that he's pushing this way, but it's got to be smaller than 8.96 because it's got to be between 0 and minus 8.96. Or interplane with J less than or equal to 151. Okay, so that's the answer. Let's have a little think about what's going on here. So he could be pushing that way with a magnitude of force less than 8.96, because it's got to be greater than minus 8.96. So let's just check our equations work for that, because it seems a little bit odd, and we want to just go through that and check. So the minus 8.96, if I had minus 8.96 in this equation, that minus 8.96 would actually just mean I've got plus 8.96 sine 30 here. So I'd actually just have, that would be my J, and it would be 8.96, and my 30 degrees are there. So if I'm looking at forces up the plane, then it's going to be 8.96 sine 30. So that would be 8.96 sine 30 here, which when it goes to there would be minus. So that seems okay. And over here, my J is here, and if J is minus 8.96, if J is a negative number, then that just means it's this way with that negative number, and that's saying the forces up the plane are going to be F and a negative J cos 30. So actually that's positive J cos 30 on this side. So it's going down the plane with 8.96 cos 30, and that's what we have here, down the plane with 8.96 cos 30. So there's no loss of integrity with this, having this as negative. That's fine for us to have. And actually going back right to the start, here this equation seems to suggest that J can be any positive number. So long as it's bigger than minus 8.96, then we're fine. This J can be anything. But actually that is only in the case that the friction is up the plane. And the friction's only going to be up the plane when, if we take away the other forces we take away the friction, the forces acting down the plane, let me put that over there, the forces acting down the plane are bigger than the forces acting up the plane. So we're only going to be in this situation compared to this situation with the friction up the plane when J cos 30, so this bit, is less than 6G sine 30. So if I do, J has got to be less than 6G tan 30, which is actually 33.9 newtons. So this was only true when J was less than 33.9, and this is true when J is bigger than 33.9. So here, really, we have that J's got to be less than 33.9, and here we've got 33.9 to that. But it doesn't change our actual end answer that Josh can be pushing to the left so long as it's less than 8.96, and he can be pushing to the right so long as it's less than 151, and the particle will remain in equilibrium.